Yeah.
Hi everyone, my name is Youping, and I'm glad to give a presentation today. I'm here to present a summary of my visiting international student program at the University of Wisconsin-Madison, focusing on the research I conducted and the courses I took during this program. I will walk you through my independent study project in HD printing and the key things I learned from the other three courses, which are decision analysis, data analytics, and image processing. This experience has been really valuable for me, and I'm excited to share what I've accomplished and learned. I want to start with a brief overview of what I've been covering. My semester had two main components: a research-focused independent study and three regular courses. The independent study was where I worked closely with my mentor, Dr. Jiang, on a project involving HD 3D printing. The other courses I took were ISyE 516, which covers decision analysis, ISyE 412, which deals with industrial data analytics, and ISyE 533, an image processing course. I will discuss each of these in turn, but let me begin with the independent study. For my research, you can think of it as having three major components. First, I read a few papers on HD printing to ground myself in exciting research. Second, I work on curved surface construction and 3D scanning, basically creating and scanning those curved sample models to get accurate digital representations. Third, I did point cloud processing and pattern projection on the 3D surfaces. I generated a cloud of points from the scanner data and then mapped a flat pattern onto the curved surface defined by those points. Each of these steps were crucial. The literature reading shaped my approach, the scanning gave me the necessary data, and the pattern projection set the stage for applying our printing technique. At the beginning, I spent time reading a relevant research paper. This paper addressed the challenge of printing a 2D pattern onto a curved surface using HD printing and developed velocity adaptive methods to overcome it. The authors developed a point planning technique where a key nearest neighbor algorithm is applied to calculate coordinates of printing trajectory points. They also designed a control system adjusting each point's height based on the nozzle's distance and the surface angle at every spot. They also created a theoretical model linking the print head speed to the curvature of the surface, which told them how to vary the printing velocity as the surface shape changed. Reading this paper gave me ideas and deeper understanding of how to approach my research, and it was really useful for my own project. When I presented this paper, I focused on the two main reasons why a constant printing speed isn't ideal on curved surface. First, the stability of the time cone is compromised when printing at a fixed speed. The second issue was uneven ink deposition. With a constant stage speed, the relative motion between the nozzle and the curved surface is not always identical, so some areas ended up with too much ink, while others received too little. This problem made it clear why the authors proposed adjusting the printing velocity based on the surface curvature. It keeps the HD printing process stable and the ink deposition more uniform. The paper also described a demonstration comparing constant and adaptive speeds by printing a snowflake-shaped circles on a natural cone shell. They did manage to print the pattern using a constant speed, but the cone turned out to be a fairly easy surface. Its curvature was gentle and quite uniform. Because of that, the benefits of adaptive velocity didn't really stand out in this example. When printing on complex surfaces, especially those with significant and uneven curvature changes, frequent speed variations can lead to reduced printing efficiency. Therefore, we aim to ensure efficient printing by controlling voltage characteristics such as frequency. For a hands-on learning exercise, I did a small experience with a Youping Pop 2 3D scanner. The goal was to understand how the scanner works and what the data looks like. I scanned a ginger without using a turntable to get good results. I tried different settings and found that a resolution of about 0.1 millimeters captured a lot of detail without remaining too much noises. After scanning, I exported the point cloud and wrote a short Python script to examine the data. This exercise taught me how to fine-tune scanning parameters and handle the point cloud out from the scanner. The scan of my test object produced a point cloud with roughly 521,000 points. The average spacing between these points were on the order of 0.06 millimeters, with a standard deviation of about 0.03 millimeters. These statistics give me a better understanding of the scan's quality. In addition to scanning, I also needed a real curved surface to work with, so I used SolidWorks to design some. By following a few tutorials, I became comfortable with the SolidWorks and created a variety of test shapes. For example, a corrugated plate. I tried different modeling approaches. Some models were made by cutting into a surface to form regular curved shapes, and others were made with uniform functions to form more irregular curves. Having these physical samples were very useful because I could then test the scanning process and pattern projection on known shapes that I have created here. After creating these physical models, I scanned them to see how well we could capture their shapes. I set a fine resolution about 0.1 millimeters point spacing of the point cloud and generated a detailed mesh with roughly 0.01 millimeters edginess. The scans of the models, while plastic models, came out nicely, giving me accurate digital versions of those surfaces. However, I ran into troubles with models made of transparent materials. The scanner just couldn't pick those out well. This is a known challenge in 3D scanning, so while these transparent models provided a low performance, so there are still problems remain as unsolved issues. The final step was to project a 2D pattern onto the 3D surface I have scanned, and I used Blender for that. I tried two different patterns. One was a U.Medicine W logo, and the other was a simple cross-hatch pattern made of perpendicular lines. Using Blender, I matched each pattern onto a few chosen 3D surface models to maintain high detail in the projection and meet the needs. I made sure the sampling is uniform in the X1 plane, points only about 1 millimeter apart. This process helped me visualize exactly how a flat designer would wrap around a curved object. And the final, with hands-on work wrapping up, I've been looking ahead to publishing these results. My immediate focus is on writing a research paper that brings together all the parts of my work in modeling, scanning, and pattern projection. We also plan to submit this paper to a journal by May 2026. To write my part, I'm reading papers from major conferences in the field to get my writing style and organization. We are aiming to publish new insights on high precision HD printing on curved surfaces, and getting this paper out will be a great accomplishment that I'm working hard toward. As part of my future plans, I'm going to incorporate computational simulations. Some details of these simulations still need to be worked out, and I will be coordinating with Dr. Jiang as I refine the approach. Importantly, after the VISP semester ends and I return to my university, I plan to continue working on these simulations and on the paper remotely. I've been committed to following through with this research and doing my best to achieve meaningful results. Now I will turn to my first regular course, ISyE 516, Introduction to Decision Analysis. This course taught me how to use structured methods to improve decision-making in complex situations. We learned to build models capturing the key elements of a decision. For instance, we drew decision trees to map out choices, uncertainties, and outcomes. We also learned to do one-way sensitivity analysis varying one assumption at a time to see how it impacts the decision outcomes. Another part of the course was understanding how to properly frame decisions, which is crucial for building realistic models. This course was challenging since it emphasized conceptual understanding over calculations, but also very rewarding. And for my group's final project, we applied our decision analysis tools to a real-world case, IBM strategy crossroads at 1993. At that time, IBM was in trouble financially, and the new CEO had to decide whether to keep IBM as one unified company or split it into smaller independent units. We modeled this decision by outlining the two alternatives and identifying key uncertainties that could affect outcomes. We built a decision tree to map out the choices and possible consequences. I helped construct the tree using a mirror and contributed to the sensitivity analysis. This project required a lot of meetings and effort, but it demonstrated how the concept from class can systematically model a high-risky business decision. The next course I want to talk about is ISyE 412, Fundamental of Industrial Data Analytics. This course was about using data to drive better decisions in an industry or business context. I covered the foundations of data analytics, different types of data, statistical methods, and data mining algorithms. Through this stage, I learned how to approach a problem by identifying relevant data and choosing appropriate analysis techniques, then implementing a solution and interpreting the results. For the final project, I was responsible for a question about travel destinations. What country would it be best for an individual to travel depending on the utility for certain socioeconomic factors? I gathered data from the World Bank and focused on 5 attributes for each country: popularity, using tourist arrival numbers, environmental quality, safety, cost, and economic development measured by GDP per capita. I normalized the data for these factors to make them comparable. Then I created a model to score each country for a given person's preference profile by weighting these 5 factors according to what that person values. And the first profile I created is risk-averse families. These imagined families cares a lot about safety and environmental quality, and much less about popularity or cost. Safety was given the maximum importance. For example, a weight of 10 here and environment a 9. With those performances, the model's top strategic destinations were countries like France, Spain in Europe, Japan in Asia, and the United States. The second profile I created was the budget traveler. For them, cost was given the highest weight in our model. When we ran the numbers with those weights, the countries that came out on top were Turkey in Europe, Malaysia, and Philippines in Asia, and Paraguay in South America. These destinations all tend to be less expensive for travelers, but still providing safe and enjoyable experience. Our third profile is social seeker. This traveler is willing to spend more for rich social experiences and high-quality services. For those social seekers, price was given a very low weight, while tourism arrives at GDP per capita was given higher weights. With such weights, countries like France and the United States and Spain emerged as top picks. And my fourth course is ISyE 533, image processing, which combined hands-on work with the math behind images. Early in this course, I used math to perform simple operations like rotating and scaling images just to get comfortable with how digital images are represented. Then I moved on to more advanced topics. I learned about nonlinear filters for enhancing images or release analysis, and we studied morphological processing using operations like erosion, dilation to clean up image as meter patterns. I also moved on to learn the Fourier transform and image segmentation here. Explore the image segmentation method to automatically separate an image into meaningful regions. And for the midterm group project, our team applied these images including techniques we learned from the class enhance our understanding. We developed a program to count the numbers of kernels in an image and to record some information about each kernel, such as its color and coordinates in the image. This involves several steps of processing. We use non-adder filter to reduce noises.
5 minutes.
To wrap up, I want to reflect on my overall experience in the VISP program. In the last few months, not only had I expanded my technical knowledge across different areas, but I've grown more confidence in my ability to study abroad in an English-speaking environment. This semester challenged me to step outside my comfort zone and tackle a variety of projects and coursework. As a result, I felt more prepared and determined than ever to pursue graduate studies. I'm particularly interested about fields like machine learning, robotics, control system, and optimization. Overall, my this semester at UW Medicine has been extremely rewarding. I deeply cherish this hard-earned opportunity, and I sincerely thank Professor Qin, Dr. Jiang, and other faculty and classmates for the help in both my life and study. And that's all. Thank you.